Here's our next problem using relative motion analysis, and it looks a lot like the crank slider we did before. But if you look at this, if you let this thing go all the way around, and if this is done roughly to scale, what you quickly will realize is that if this goes too far, it'll lock up. There's no way this can turn all the way down because this piece is too small. These things can be used for various reasons. But this is mainly educational. So here's the mechanism we have here. So I have a 0.3 meter crank that can't go all the way around, but it's at 45 degrees. And currently, angular acceleration is 0, and angular velocity is 4 radians per second counterclockwise. Here we have a pin at B going to a 0.125 meter coupler, and then that heads off to the slider, and this is currently at 45 degrees. And so the problem is simply determine the velocity and acceleration of this slider. So let's go for that. So again, we're going to always start from what we know and kind of move to what we don't know and what we want to find out. We know everything about this point, so we're going to go from here, which is called A, and we're going to head to B. So we can, here we are, just getting oriented. So VA, it's 0. Boring. Okay, so from here we go 0 plus, and to go from here to there is simply omega cross R. So we have omega ABZ, well, and we know that's 4, cross this length, and then here's the orientation. So 0.3 times cos 45x plus sine 45y. It's in the plus x direction, the plus y direction. Now if I do not have x and y on here, it is always then assumed to be the normal xy. X go this way, y goes up. Okay, given this, there's a z cross x, a z cross y. That's all given here. I'll let you check all of that. But whenever you do velocity, I encourage you just to look at this and say, does it make sense? This is going this way, so b is going like so. So that's going to be a negative x and a plus y. So just check the signs. If they don't match up, then you can go, okay, I know I made a mistake. So there's the acceleration, or the velocity of B. So now we're going to go from here, and we're going to get the velocity of C. Now, let's just take a look at this, though, and say, is there anything we can use? This is a slider. It can only translate. So the velocity of C will be along the x. And looking at this, it's apparent it's going to be in the negative x direction. So we know what we expect. So when I go to get the velocity at C, I can do this two ways. I can go from B to C, and then I can also use the geographical information that says this is going to go along the x. So that's reflected here. So I know my answer will be VC along the x, and I expect VC to come out to be a negative number. I can also go from velocity of B, which I just computed, and then through omega cross R, go from B to C. And that's what we're doing here. So here was the velocity at B plus omega VC, which we don't know. I'll assume it's counterclockwise positive, but we'll just see how it works out. Whatever sign is there, you'll know from that. This will be, so here, omega VC Z cross the length, and then here is simply the orientation. Now look at what's happening. Minus 0.707x, because it's cos 45, sine 0.707y going up. All right, so then given this, we can simply equate the y's, because the y's are 0. So on this side we have a 0. Equate that to the y's over here, and that will tell us omega VC. Then we'll go look at the x-axis along the x, and then we can determine VC. And so that's what we have right here. Equating the y's, 0 equals the y's on the other side. We get omega VC as 9.6 radians per second. All right, very straightforward. Equating the x's, we can solve for VC. And we wind up with minus 1.7x. and that makes sense. We could always have an algebraic mistake in this number, but the fact we're along the negative x, we feel good about that. So we've got all the velocity stuff done. Now we got to do the acceleration stuff. So let this much show, and so let's do acceleration of b. So we're going to go from a to b. Acceleration of a is 0. It's pinned. So from there, it's simply alpha cross r minus omega squared r. But here we have a nice piece of information. Our angular acceleration is 0. So that gets rid of this whole term. All right. The omega squared, we know that from the velocity work. So we can just put that in. Boom. So here's minus omega squared, and then RAB, 0.707x plus 0.707y. Multiply that out, and here we have the acceleration of b. Since there's only a normal component, notice it comes back in along the x and y. So it's negative y, negative x. So we have that. So given that, now we can just do the logical thing and go from b to c. Now once again, we can look at this and we know any acceleration here is only going to be along the x. All right, so if we stick our numbers into this, AC is going to be a component of the x plus 0y, and that's equal to the acceleration of b plus the relative acceleration of c relative to b, which is alpha cross r minus omega squared r. Drill that into you. This is the unknown. We don't know alpha bc. The normal acceleration comes from velocity, so we always know this term. We should always know this when we get here, or we've forgotten to do something. So alpha bc is an unknown, and then AC over here is an unknown. So what's going to happen? We're going to substitute everything we can in for this, do the cross products, and then we'll have an equation relative to x, an equation relative to y, and that's the one we'll do first. So when we use the equation for y, we'll figure out alpha bc, then we'll do the x, and that'll give us AC. All right, so I stuck all the numbers into here. That's what's happening here. I'll let you check that. You do all the cross products and separate it out into y and x. Here's the y term, 0 equals the other y terms. That tells us alpha bc is minus 130.7 radians per second squared. I will note, it's not unusual to have very large numbers in here. Okay, so don't let that bother you. X, taking this, substituting in, solving for x, we get AC is 16.22 meters per second squared. So what that's actually saying, notice that's a positive number. So what this is saying that it's accelerating this way. In other words, it's moving in this direction, but it's slowing down. So it's getting ready to flip the other way, ideally. Okay, so there's our analysis of this problem.